Okay, well, let's get started. It's a pleasure today to welcome Jason Dexter. Jason did his undergrad degree just a few miles from here at Occidental College, and then he went back home to University of Washington, where he did his PhD with Eric Agol, the former postdoc here at Caltech. I note that for the mathematicians in the audience, Eric's brother Ian is probably more famous and was actually an undergrad here, identical twin brother, was an undergrad here. Anyway, during his PhD, Jason studied problems with microlensing of AGN accretion disks with Eric Agol, filtered accretion disks, and quasi-periodic oscillations in black hole X-ray binaries. But the main part of his 2011 PhD was on radiative models of Sagittarius A star and M87 from relativistic MHD simulations. And that included both simulating the accretion disk and realistic visualization of the disks in Kerr geometry. But after his PhD, he was a postdoc at UC Berkeley, and then the leader of a research group at the Max Planck Institute for Extraterrestrial Physics in Garching. And in 2019, just in time for COVID, he joined the faculty at University of Colorado Boulder, where he's assistant professor of astrophysical sciences, a fellow of GILA, and a coordinator of the Event Horizon Telescope Working Group on Modeling and Theory. And he got an Alfred P. Sung Foundation Award in 2020. Jason is notable for keeping close connections between observation and theory, both predicting observable phenomena and then helping in the interpretation and modeling of the data. So besides his very long career on relativistic MHD simulations of the black hole accretion in M87 and Sagittarius A star in the service of the Event Horizon Telescope, he's also worked on simulations of accretion and jet formation in X-ray binaries, applications of precision infrared interferometry, i.e. gravity at MPE and Garching, to study accretion disk layers changing with quasars and measurements of the orbits of binary quasars and stars in the galactic center. And today he'll tell us about black hole accretion from the inside out.
Okay. Yeah, thanks so much for the nice introduction and the opportunity to speak today. So yeah, this will be a talk about astrophysics theory of this problem of black hole accretion, in particular, trying to understand some unsolved questions in accretion theory by looking at what can we learn from looking right next to the event horizon and images of black holes down here, and then trying to apply that to other systems in the universe, since we can only actually do those measurements in 2 cases. So I'll discuss those results that are done as part of large collaborations, the Gravity and Event Horizon Telescope collaborations, and I've also put on the slide the names of students and postdocs that have taught me a lot about this over many years. Okay, and the other thing I want to say is that I realize it's a physics colloquium and a mixed background. I'm going to talk about an astrophysics topic, so please interrupt me whenever there are questions or clarifications or whatever you would like to know. Okay, great. So let's get this to work. Okay, great. So accretion is the process in astrophysics where material falls onto some central object. So this could be like a star here with material being stripped by some compact object down here. And the general reason that we care about these in astronomy is it lets us see systems that we otherwise wouldn't necessarily see. So the energy from the infall of material, that gravitational energy, can eventually become heat and radiation, electromagnetic radiation that astronomers observe. And we generally think of these systems as being rotating, but the gas should either fall from stripped in the case of a binary system or falling from far away. And either way, it should have some angular momentum with respect to this small compact object target in the middle. And so it should probably get rotationally supported at some distance. And in addition, we think that this is ionized gas, certainly in the case of black holes, and it's rotating and it conducts magnetic fields, and the combination of rotation and the magnetic field seems to produce these jets that we'll show on a slide in a minute, very commonly associated with the accretion process. Okay, and objectively speaking, today, black hole accretion is the best case of this. The central object can be anything. Black holes are the best. And the reasons for that are manifold. So black holes have the deepest gravitational wells. And this allows, for example, that black holes power the brightest persistent objects in the universe, in quasars, despite not emitting much themselves. And the other thing is that if you want to study what happens close to a black hole event horizon, for example, to probe the space-time, this is a great opportunity with accretion, because most of the radiation comes from where the gravitational well is deepest, which is right near the event horizon of the black hole. And the other thing that we'll discuss today is that because black holes have no hard surface, this problem ends up very rich and complex. That the energy can either be radiated and power these extremely luminous objects we see across the universe and quasars, or it can all just be lost through the event horizon of the black hole and not radiate much at all. Okay. Great, so we have a standard theory for how accretion should work, which is now 50 years old. And the standard accretion theory in this way is this axisymmetric stationary set of hydrodynamics equations. And the remarkable, and this describes a situation where the gas is assumed to usually be rotationally supported. So in what we call Keplerian motion, test particle orbits around its central mass, and only slowly in spiraling with what's usually assumed to be some constant flux of mass. So things are marching inwards, but slowly over time, and mostly hung up in rotation. And if one solves these conservation laws with some simple assumptions, the remarkable thing that came out of this early theory, and the major reason this is still used today, 50 years later, is that you can actually predict the types of black hole sources accreting that we see in the universe. In particular, that we see small black holes in our own galaxy, stellar mass black holes, 10 or so times the mass of the sun, and these appear as X-ray objects. This is an X-ray spectral energy distribution, power, total radiated power per frequency, and peaking at X-ray energies. And whereas supermassive black holes, this is thermal radiation, by the way, so optically fixed, a thermal radiation coming from a surface near the inner edge of the disk. And if you go to supermassive black holes, even though they're radiating far more energy, they appear at a lower photon energy, so at optical UV energies, because basically the radiating surface area is larger. Okay. And so this theory explains how you can get very luminous accretion, like in these examples here, and why these sources appear where they are seen to be. Okay. There's a couple of basic problems with it right away, which is that this doesn't explain actually how the gas falls in the first place. We said the gas is rotationally supported. That should just go on forever. There's nothing to make the gas fall off of its orbits. And so this is just parameterized in these models in a simple way that there must be some torque in the disk so that the gas can actually march inwards at all. Not explained in this picture. And similarly, there aren't jets or anything else like that. Okay, so one topic for today is that all of these phenomena shown here in this schematic picture over here, and in this real image of jets on galaxy scales coming from a black hole way down in the center here, all of these are associated today with magnetic fields. And we would like to go and observe those magnetic fields. And so I'll try to argue that we can actually learn about these magnetic fields from black hole images and try to learn how are these magnetic fields actually causing gas to fall in and accrete, and how are these jets being launched. Okay. Great. The next thing is that in standard theory, as we said, the black hole doesn't have a surface. And so the way these things can look can really depend on basically how much gas is available to fall in from somewhere in a galaxy, from a stellar companion, and so on. And we usually think of this divided into two categories. Again, going back to venerable standard theory. So this is the case we were talking about of accretion disks over here, when the mass supply rate we parameterize with this little m dot here, which is a order unity for very luminous accretion disks, and can be much lower than that for cases like the center of our galaxy in M87, where we image the black holes. But when this rate is high, meaning order unity, then the gas can cool very quickly compared to how long it takes to fall in. Okay, and so this means that it will be very luminous, it will radiate away a lot of energy, and so it will be colder in temperature. And if one then makes a hydrostatic equilibrium argument, colder means smaller thermal motions, and so the geometry will be thinner. So this is what we call a thin accretion disk over here. Very luminous, applies to quasars and X-ray binaries that we just showed. Okay, but instead, in the opposite regime, this ratio can be very different depending on the mass accretion rate, the mass supply rate onto the central black hole. And if it becomes small, then there's something that changes where the cooling time of the gas to radiation becomes long compared to how long it takes to fall in, meaning the gas can just carry its energy with it and not lose its energy. And in that case, then the gas remains hot, and so it remains thick. This h over r, the scale height of the disk, can be very large, so it can puff up into this hot structure here, lots of gas pressure with slow cooling. And this I will at least call today a hot accretion flow. And just remember, when we talk about black hole images, this is the case that we think applies over here. Okay. Okay, so at least two very different regimes of how this should work. And traditionally, we also assume for similar reasons that this case over here is the thin accretion just should power the brightest objects in the universe, persistent objects in the universe with very large, what we call radiative efficiency. So this is the statement that accretion can extract more rest mass energy of infalling material than you can get, for example, out of nuclear fusion by a large amount. So up to 10% of the rest mass energy can come out in radiation. And we generally assume that this picture should not produce that much radiation. We'll revisit this in the talk. Okay, but based on this standard theory, what we would then expect to go look at the universe is that, well, if things are accreting at small amounts, they should look like hot accretion flows. This is just a trajectory of this m dot, how much mass is falling on. So you should have things sort of stratified in how luminous they appear to us. There should be hot accretion flows, which are dim at low luminosity. And there should be these thin accretion disks that appear up here at high luminosities. To some extent, that's true. The galactic center is very underluminous, whereas quasars are much more luminous. So to some extent, that's true. But there's also some stuff that we're missing that we still need to work out here. So for example, this is a case of a single X-ray binary observed at two different times, the stellar mass black hole accreting, where the systems evolve on timescales of sort of months to years, where we can actually study their changes. The photon energy here, this is another spectral energy distribution. The photon energy here you can interpret as a temperature in both cases. This is thermal emission from a surface, and this is inverse Compton emission, but nonetheless should peak at the maximum temperature. And so this is a hot accretion flow. The temperature is something like 10 to the 9 Kelvin. This is 10 to the 7 Kelvin over here, a thin accretion disk. And this is the two states we expect to see, so that's great, but they also occur at almost the same luminosity. Okay, these are not well separated in luminosity as a one parameter thing. Okay, so we would at least like to revisit, if we had a better accretion theory, what should accreting black holes actually look like, say as a function of their mass accretion rate, other relevant parameters. Okay, great. So the major theoretical advance since analytic theory is the recognition of probably at least some ways that gas can fall onto black holes in the first place due to the magnetic fields. And the idea of this is that if you just put ionized plasma that conducts magnetic field into a configuration where it's differentially rotating, then this will tend to be unstable. The magnetic field will tend to be amplified, the gas will become turbulent, and this turbulence can produce stresses which then allow angular momentum to move outwards, meaning that the gas can then fall inwards. Okay, and this is called the magnetorotational instability, known actually for a long time, but applied to accretion in the early 90s. And this is great, we can now get gas to accrete. And the problem is that the way you need to do this, because it's a magnetic system with turbulence that needs to be sustained, then you quickly turn to computer simulations because you need a three-dimensional calculation that's time-dependent with magnetic fields in it, so MHD minimally. And that's developed into numerical simulations like I'll discuss today. Generally, the case we'll focus on today is what's called general relativistic MHD, which means we want to look at the parts with the black hole in it, so close in, capturing relativistic effects. And so we'll still solve the hydrodynamics equations like before, but we'll do this on a computational grid with magnetic fields, so MHD in a curved space-time background, which we will fix today as the Kerr metric. And the remarkable early results of this theory was showing that starting from an equilibrium configuration, some mass reservoir that you just distribute around the black hole, which would otherwise not accrete, if you put in a weak magnetic field, this instability will kick in and drive stresses and cause the gas to fall onto the black hole. Okay, and the other thing that it does is it tends to shoot jets out the spin axis of the black hole, meaning lots of strongly magnetized pointing flux comes out along the black hole spin axis. Okay. So from simulations like this, we've sort of identified two different states that black hole accretion flows can have depending on how we distribute the magnetic field initially, which we do just purely experimentally, right? We just put this in, we don't know what this should look like ahead of time. And basically the idea here is that if we put in a relatively small amount of magnetic flux, so out of the orbital plane magnetic field in the initial condition of how we set up a gas dynamic simulation, if this amount is small, then we get something very turbulent, like shown here. The accretion here is clearly driven by this magnetorotational instability, and it has relatively weaker magnetic fields. And instead, there's kind of a limit where the black hole will only accept so much magnetic flux. And if we put in a lot, then it will saturate and reach a state that looks more like on the right, stronger magnetic fields, somewhat more ordered, and with really powerful jets. So this jet region over here, this is density again. So these colors are high density, this is low density, sorry, and this is the black hole here, and this is the vertical direction in a slice through a 3D distribution. So the jet comes out over here, and these purple regions are sort of associated with the jet, and these are magnetic field lines in the black. So this produces a very powerful magnetosphere and jet from the black hole over here, compared to this case over here. Okay, so the magnetic fields, depending on what we do to start with, even when they're weak, can become dynamically important and start to push back on the accreting gas and cause it to change how it accretes. And because, again, in the universe, real black holes are accreting from very large scales, we can't usually put in the full initial condition of what happens at larger scales. So currently, this is sort of a priori unknown which of these we would favor in real systems in the universe. And so something we'll try to do today is sort out between them using black hole images. Okay, great. So, yeah, please.
So in this, for like neutron stars, what seems to happen is that you start, whether you start with colloidal or toroidal, after 20 to 40 milliseconds, the magnetic field reaches some turbulent state, and this is hand wavy, roughly independent. How sensitive is this to like the exact, do I use this shape of magnetic field but have this flux in these simulations? Has this been looked at already?
Yeah, it's a really good question. So the question is basically, how much do the details? So in this experimental approach, one hopes that the result you get does not depend on what you set it up with, because you know you didn't start with the right thing like we have in the universe. For one thing, we need to start really close to the black hole, something like 100 gravitational radii, whereas say in the center of our galaxy, the gas is coming from more like 100,000 gravitational radii. So you hope to reach a state that doesn't depend on the details of what you set up. This is one example of something that we know depends on what we set up. If we supply a lot of magnetic flux, it will saturate and produce a different, just qualitatively different looking solution than if we don't. But then the question is, well, what about all the other details of what you did? I don't know, do you put in lots of little loops, or do you put in one big thing, or how do you, or is it all vertical or whatever? And that, I think, to me, this is the part I know matters. The other parts is less clear. I would say there's no clear evidence that it matters in detail, but yeah, it's hard to give a definitive answer. Maybe next time I give this talk, there'll be two things, and there'll be 3 slides, or 3 pictures. And so it's a good question. The hope is that this definitely matters, right? The hope was that nothing would matter. Now we know that at least this matters. Yeah, and hopefully there aren't too many details like that do more. The other one I would highlight that I'm not going to talk about today is if the gas, here we're assuming the gas rotation axis aligns with the black hole spin. The other one we know definitely matters is if we misalign those directions, that will do some different things depending on the rest of the problem. So I'm happy to talk about that more. Yeah, not going to address it in the talk. Yeah.
So you're saying the gas, are you assuming that this is a weakly ionized plasma or fully ionized plasma?
Oh, thanks. Yeah, so gas around black holes is really hot. So we wrote down that virial temperature from if you just assume it's gas pressure supported. So in this case of a hot accretion flow, like we're going to do for black hole images, typical gas temperatures are something like 10 to the 11 or 10 to the 12 Kelvin near the black hole. So it's very, very hot, very ionized gas. At event horizon scales, the virial temperature for gas pressure supported material would be about 10 to the 13 Kelvin. Yeah, and even in the cases of these thin accretion disks that are cold, quote unquote, when I say cold, I mean more like 10 million Kelvin. So being ionized is a very good approximation in black hole accretion. Another strength of black hole accretion. The equation of state is generally less complicated, with the exception probably of quasars, where things get hard again. Okay, great. Any other questions? Okay. So we've developed now a numerical theory of accretion. You might want to know, well, does this describe anything that goes on in the universe? And this is something that as Sterl said, I was interested in my PhD what are good ways to test this? And there's a variety, but one of the best ways I think is in the case of black hole imaging that recently became possible. So what we set out to do then is to apply these models to 2 systems, the galactic center black hole, Sagittarius A*, and M87, which are the 2 black holes that are the biggest on the sky. So in angular size, meaning the most accessible to being imaged. And these are both hot accretion flows accreting at very low rates. But the basic idea of what we do then is the advantage of doing this approach is that we can actually do a time-dependent and fully relativistic calculation of what these things should look like. And in particular, we include the dynamics of the magnetic fields, which give rise to the synchrotron radiation that we observe from these sources as their predominant way of radiating, and certainly in the black hole images. Okay. So the approach here is that you take something, coordinate frame visualization of, let's say, the log density of the gas looks like here. We're getting the spin axis is up here. This is the radial direction out here. And then you can calculate, well, what would synchrotron emission be if I scale the parameters to what I expect for these systems, meaning like, say, the accretion rate to this number, choosing essentially the density scale of the gas. And then you can see, so this is coordinate frame here. And then you can calculate with all relativistic effects. If I look at this as a distant observer, what should I expect to see? And summarizing a lot of work in this area, we realize typical conditions like this. So there's these very hot electron temperatures here, but also gas temperatures, very, very, very low densities, and magnetic field strengths of something like 10 or so Gauss. Okay. And so summarizing all of that work, the main conclusion is that if you look at these things at the peak of their radiated spectra, so at where the Event Horizon Telescope observes where we can image them, then what we expect to see is that the emission should come from right near the black hole. So this gas distribution can be very extended, but actually the emission comes from close in. This is good for us because we're only actually modeling the gas very close in. And the other thing is, because it's close in, the images we expected to see should be shaped by relativistic effects. And in particular, the things that matter are the light bending, gravitational redshifts, and the Doppler shifts. So the images that we predict generically look kind of like this, where this bright region on one side is from gas approaching us. So the rotation is going away from us on this side and towards us on this side. And that's due to the Doppler beaming effect. The rotation speeds are a significant fraction of the speed of light. And then this dark region in the middle is the so-called shadow of the black hole, corresponding to, if you trace photon orbits from far away, the ones that intersect the black hole event horizon. And that'll tend to have less emission because it had to come from in front of the black hole rather than some other location. Okay. Yeah.
So here what we're looking at is sort of slightly above the edge. So what we're seeing in the top is the disk behind.
Yeah, thanks. These images are interesting in this way. Yeah. So this is coming from in front, and this is actually coming from behind the black hole, from light that's bent up and around and towards us. So yeah, you can see behind the black hole in that way.
Would jets be bright enough that you could distinguish between jet and not
Yeah.
jet, or like maybe this is the next slide.
No, this is a great question. We have this ongoing debate about, in the real images, are you seeing the jet or are you seeing the disk? So my impression today would be that in general, this is probably infalling material, or at least not highly magnetized jet material, like for instance, you see from M87 on really large scales. But if the material is actually infalling or outflowing, it gets a little complicated. Everything's very close to the event horizon, and so it gets a little complicated. But thanks. Happy to talk about that more too. Okay, great. So this is kind of what we expected to see. And the amazing thing is that we can now make these images. So I just briefly wanted to show that the Event Horizon Telescope that I'll talk about first, one of these experiments doing black hole imaging. This is observations from last year. This year's observations just ended a week or two ago. But basically the idea of this experiment is to combine all of the premier millimeter observing facilities around the world and carefully record signals, combine them later in very long baseline interferometry, and so make a virtual telescope the size of the Earth, observing at the shortest possible wavelength that can be done from the ground. Okay, and this naturally involves a lot of telescopes and a lot of people, at least by astronomy standards. This is a picture of the collaboration. We have something like 300 people doing this work. Okay, and the remarkable results that we now have for both targets that we can currently do with event horizon scale resolution is that the images both show what we think is the shadow of a black hole, meaning that both in M87, the first came out over here, this dark region in the middle, and this dark region in the galactic center black hole, we think that that corresponds to the shadow of the black hole, this region where light trajectories from far away intersect the black hole event horizon. Okay, and this image especially, so this is a remarkable technical achievement in being able to do this. These images also have sizes compatible with what you would expect, especially in the galactic center, where we otherwise know from orbits of stars around the black hole how massive it should be and where the center of our galaxy is. So this really nicely matches the size you should expect for this feature, as well as the shape of the image that you would expect. Okay. But also, especially in the case of this M87 source, you can see there's this asymmetry. And so this really matches what we thought the theoretical expectation would be for these images. So we think we understand what we're seeing. And in particular, if you take some theoretical model, it's very easy to find cases that look kind of like this thing in the middle, which is a very high resolution theoretical image from one of those GRMHD models, numerical simulations we were talking about. And you can sort of convolve this with some appropriate beam, and it makes an asymmetric ring image a lot like the ones that we observe. Okay, so again, we think we understand what we're seeing in the real image, and maybe if you could do, enhance a lot on this, maybe it would look something like this here. In particular, that we think that this brighter region corresponds to gas rotating, so coming towards us. And in M87, this is consistent with the jet that we see, which is pointing out sort of in this direction over here. So the bright spot should be perpendicular if the material is rotating and the rotation axis lines up with the jet axis. Okay, was there another question? No.
Ask about the viewing angle. I've seen the center image a few times, and I'm not sure where the viewing angle is relative to the disk.
Yeah, so in M87, we're mostly looking down on the jet, which is why the jet appears as spectacular as it does, because of the Doppler effect from motion coming at us. So we know that that's at what we call low inclination, meaning we're mostly looking down on the gas. So that's why the Doppler effect here is pretty subtle, even if clearly detected. It's not a very strong contrast because we're mostly looking down on it. So that was the prediction. And then the jet points out this way, but mostly it's coming at us out of the screen. Does that help? Okay, great. Okay, we'll come back to the galactic center in a minute because it's a little bit confusing in this way and interesting in this way. Okay, great. So the other remarkable observational result in this area that we'll try to, at least I will suggest a possible theory for, is that if we look in the galactic center, it's highly time variable. That's the reason, one of the reasons that the image looks a little strange. It's very difficult to reconstruct images of our galactic center black hole because the source structure is very clearly changing on timescales where you would like the Earth to be rotating so that you can try to reconstruct an image of it the way that we do interferometric imaging. Most spectacularly, we see this if we look at higher energies. So instead of looking at millimeter wavelengths, if we look at infrared and X-rays, we've seen for a long time, what we call flares. This is the brightest infrared flare from the UCLA group seen with Keck, where suddenly the source brightens by some tens of times in luminosity. So these things are stars, and the black hole pops out there all of a sudden. And this elapsed time here is something like a couple hours for the whole animation. Okay. And so the idea with interferometry, what we can do is not just look at changes of brightness of a source in time, but try to actually watch it move over time. So we try to pinpoint the center of the light and watch it move. So this isn't quite imaging, but it's spatially resolving the motion of the flaring source over time. And these observations are done with the gravity instrument in Chile. So now instead of using very long baseline interferometry, these are 4 to 8 meter telescopes that are connected using tunnels under the ground and combined at this central location in an instrument to do interferometry. So to make a virtual telescope that has this size here, something like 100 meters instead of 8 meters of each telescope. And the remarkable thing from 3 flares in 2018 is that what we see is that the center of light of the flaring region moves coherently on the sky. This is the best example showing this move over about 30 minutes from here in red to orange to green to blue. So coherently rotating around some location, which is consistent with the location of the mass of the black hole in the center of the galaxy. And if you put this together, it's moving at apparent speeds of 20 or 30% of the speed of light at a projected radius of something like 3 or so Schwarzschild radii. And so you can infer a central mass, which is totally consistent with the 4 million solar masses that we know are there from stellar orbits on larger scales in the galaxy. Okay. The other striking thing about this is that if one bravely and boldly just puts this, there's no registration between these 2 pieces of data that I've just done, so be careful with that. But if one does nonetheless just put the points of that motion on top of the EHT image, they're at least compatible with being on similar spatial scales as each other. And the other really weird thing that we thought at the time, this was from 2018, the other really weird thing that we saw here was that there was no clear signature of Doppler beaming, where you would expect that at some position on the sky, the flaring source should get much brighter because it's pointing at you. And there was no such signature. And so similarly, this image does not show any clear asymmetry, like one side being brighter. So seemingly, this is all consistent with a picture where we're sort of looking down-ish at the gas in the center of our galaxy. Okay, yeah.
What contributes to the strange shape of this orbit?
We did our best. It's hard to measure. No, I don't know. It's a great question. I think it's consistent with an orbit. So if one fits this with orbits, that the shape of this is not like a major discrepancy. There's no major issue to solve. But I would just say in general that we're talking about gas motions. And so one should be a little careful of whether this is really, coherent rotation of like one thing on an orbit. Right? There's a lot of forces that can apply to gas. I said it's consistent with the mass of the central black hole, meaning it's purely gravity, but there are lots of things that can make things move at significant fractions of the speed of light close to a black hole. Right? So I think there's some interesting open questions about, what should this really look like? Yeah. Is it as simple as that? Because I don't really know how you get something to flare and just go around simply around the black. Anyway, I'll show what I think it is in a minute. Okay, great. Okay, so maybe these things are related to each other physically in some way. It'll be interesting to see how that goes. Okay, but I just want to say that we said that we would do accretion physics in this talk, so I'll come back to flares and trying to explain flares that might occur from this. But actually, the shape of the total intensity images with the HT is fairly generic. We argued that this is kind of set by relativistic effects near the black hole. And so it's actually pretty tough if you want to know, oh, what's the spin of the black hole then? Or, oh, are the magnetic fields weak or strong? Or, oh, how's the gas rotating relative to the black hole? It's really hard to tell just from these images because this prediction of that these things should look like these asymmetric rings is really robust. So you change things in your model and recalculate images, change the way the black hole's spinning, change the initial conditions of the calculation, and you can at least find examples that match one image where these show these same basic features. The images are different, clearly, and the data can tell them apart, but it's not that one of them has some signature that, aha, this must be the spin, for example. Okay, so this is really hard to do, so we should do something else. And so this is my, oh, yeah. Yeah, so I think this is prograde, 0.9375. This is retrograde, so the gas is moving the other direction, but around 0.9375, and this would be 0 here.
Surprising that prograde, the ISCOs are very different in the two cases.
Yeah, right. So that's right. So often in thin accretion disk science, there are estimates of black hole spin, and this is done by finding some feature which traces the innermost stable circular orbit. Because we said that gas is very slowly inspiraling, it's mostly just orbiting. And that will then have a very sudden transition where once you reach the innermost stable circular orbit, that's no longer possible. So there's a very sharp transition where the gas goes from orbiting to plunging into the black hole. And so you often find an edge of a disk. In hot accretion flows, we don't tend to see a strong signature of an inner edge, mostly because the gas starts plunging and does it very smoothly from far away. But that's right. And in the calculations, at least, the emission, say in this case, or especially in this case, would be coming from well inside of this innermost stable circular orbit. Yeah. Another way to put it is the gas density tends to kind of smoothly increase or slowly turn over inside there, not sharply truncate. Yeah. Great. Okay. So instead, the way that we get at this today, or that I'll argue we can get at this today, is with linear polarization. So synchrotron emission is linearly polarized. And I'll argue now that this tells us about the magnetic fields. This type of argument I'm going to give has been done for a very long time in the context of jet science in radio astronomy. It's just that now we can do this right next to the event horizon of a black hole. Okay, so the way this works is that the linear polarization map shown in these white ticks for idealized magnetic field geometries clearly changes depending on the magnetic field geometry. So if I make a magnetic field that winds around an azimuthal magnetic field, these white ticks show this pattern. Whereas if I put in a purely radial magnetic field, this is just an idealized toy model, not a real calculation. but this shows this type of pattern here. And even though the total intensity images in the false color in the background look at least fairly similar, at least look like rings. Okay, so the magnetic field configuration from synchrotron emission will tell us about the way the magnetic field is oriented around the black hole, will be imprinted in the synchrotron emission. And this is because synchrotron emission is emitted perpendicular with a polarization perpendicular to the line of sight direction and the magnetic field direction. The electrons are spiraling around magnetic fields, and so there's a preferred direction in polarized light. Yeah.
What is polarizing the light?
In synchrotron radiation, so it's the fact that
This is synchrotron radiation.
yeah, this is synchrotron radiation. Yeah, so that's the process that polarizes it. Yeah, so this is emitted. So I just want you to focus on the toroidal case because that's the one that we'll test in a minute. So the idea here is just that the emitted polarization you see written as P is related to the perpendicular to both the line of sight direction and the magnetic field for synchrotron radiation. And so if you wrap the magnetic field around, toroidal B will come out as radial electric vector position angle shown in the latex. So you'd expect a radial pattern if you had a purely wrapping around magnetic field. Okay, so this is sort of how you get at magnetic field direction based on the data, because we'll measure the polarization map. But then I also want to argue that just based on sort of qualitatively, what we expect is that should also tell us about whether the magnetic fields are weak or strong. And this is because if I imagine that I start with a weak magnetic field pointing any direction, if I put this in differential rotation, the magnetic field is carried with the fluid that's rotating, and it will be sheared out into a toroidal configuration no matter what I start with. So if the magnetic fields are weak, I should get that last map that I just showed you. Pointing in any other direction once I get down near the event horizon requires that the magnetic field was strong, meaning it can resist being sheared into some other direction. An extreme example of a magnetic field is shown as a cartoon here, not my proposed model, but if magnetic fields become strong enough, you can imagine that they even resist the accretion itself because they're so strong. Yeah.
For this, would you expect the magnetic field strength to decrease that as well?
Sorry, in which case?
For disks that radiate quicker.
Oh, I see. Yeah, so if the cooling is stronger, well, actually, we'll come back to that for strong magnetic fields, but actually, I would expect that if magnetic fields are strong, that they end up relatively more strong when the gas can cool. The way we measure this usually is the gas pressure to magnetic pressure ratio. And basically, a colder disk will just have lower gas pressure. So it's easier for magnetic fields to become strong in the sense of being able to push the gas around when it's colder, I would argue. It's a nuanced and very interesting question with lots to say that I have no time at all to say right now. Happy to talk about it more. Okay, great. So we can just go to the M87 Event Horizon Telescope polarized image, which is shown here. So our asymmetric ring that was in colors before is now the grayscale in the background. And the ticks are showing the measured electric vector polarization angle. And you can see this shows a twisting pattern. The length of the ticks is polarized flux, and the color coding is their fractional polarization. So something like 10% linearly polarized at the scale of our resolution, the Event Horizon Telescope. And the simple argument upon looking at this is that this is not our radial tick pattern. And so this is not an azimuthally dominated magnetic field. A somewhat more detailed comprehensive analysis so far to date is consistent with that. And so favors that there's some strong component to the magnetic field on event horizon scales near M87. Okay. So there's some, we don't know exactly where, we can't really decompose this uniquely into components, but some other component pointing in some direction is significant, at least as well. Okay, and I just want to highlight that actually there's a similar result that you can get from the Sgr star flares that I showed with gravity, where instead of doing the polarization map and just showing it like this, you can measure over time as the emission region moves around, you can measure the linear polarization angle and see that it's rotating coherently also with the motion of the emission region. And if you imagine sampling this, then that means the time domain there is basically like a spatial resolution as you go around, because you're sampling the background magnetic field as this emission region goes around, and you reach a similar conclusion. Okay, so it seems like both these sources have strong magnetic fields on scales of the event horizon. Okay, so yeah, so for the rest of the talk, I'll just give a couple examples of trying to then apply this. Maybe magnetic fields are strong near accreting black holes. What would we then expect to see in other contexts? So starting with flares from the galactic center, and then talking about what about if we try to push to higher accretion rates to get to systems other than like these two, the systems that most people, for example, here would be interested in studying and know what they might do. Okay, great. Okay, so the first thing is that it seems like if you make this strongly magnetized accretion flow numerically, what you expect to happen is that this thing should undergo recurring eruption events. And the way that I would think about this is that the magnetic field is the magnetic flux accumulates on the black hole, but that's not a hard surface. It's held there by the gas. It's confined by gas. So it's brought in, but if it becomes strong enough, then eventually it just expels outwards because it's being confined by gas pressure. If it becomes too strong, it just pushes back. It doesn't want to be confined anymore. And so this ends up numerically as a recurring pattern where the magnetic flux shown in the blue on the plot builds up, and this is put in our initial condition that it builds up, and then it undergoes these cycles, and this is a very long calculation where you see many, many of these eruptions that just repeat over and over. Okay, this has been known for a while that this will happen in strongly magnetized accretion. What we found is that these events tend to produce heating of the gas and can produce what look like flaring events. So in the black here, this is a light curve, brightness versus time in the near infrared flux if you model this as Sgr star, and these spikes are all what we would call flares from the galactic center black hole. Okay, and this kind of looks in recurrence time and duration and stuff, this looks at least compatible with the warning that I don't know what sets those timescales, so more to do. But the other thing I wanted to highlight is how this looks. This is a three-dimensional problem, so it's not simply that the magnetosphere from the black hole erupts evenly in all directions. In fact, it sort of pushes out in one direction first, and it produces non-axisymmetric sort of rotating regions that go around and would look like a rotating flaring region. Okay, so this is shown here in magnetization. This is this strongly magnetized region in purple that erupts away from the black hole and forms this big thing that goes around. And the dissipation is shown there, that the red is heating, and that thing also goes around. And if you model this as infrared flux, then you see that there's this region that goes around the black hole. Does not look like a point source orbiting in purely gravity, but it does rotate around the black hole at some speed and is at least then qualitatively similar to what we see in the flares. Okay. So this at the moment is my best guess of what flares from the galactic center are. And I think it's kind of nice that this emerges naturally when you have strong magnetic fields, which we infer otherwise from other arguments. Yeah.
This is ideal MHD with resistance.
Yeah.
Where you start getting, I realize this is sort of a big
Yes.
open question, but you get plasmoid formations,
Yeah.
current sheets.
Yeah, so there's wonderful work. So our reconnection, when we say there's heating from reconnection, this is essentially an error term in a code. There's not supposed to be dissipation. If you do ideal fluid dynamics, there's no dissipative terms in your equations. So what happens is magnetic fields have different directions, and then they have to, come to agreement across a cell boundary, and that energy is captured as heat in the calculation. So that's right. The heating term we try to estimate, and you can see the blue here is negative heating. So it's a very noisy quantity, the heating that we get in the calculation. And in general, in fluid dynamics, the reconnection rate and other things can be different than in plasma physics kinetic calculations. So there's a really interesting open question of, in a case like this, as I'll discuss in a minute, you'd like to explain X-ray flares by accelerating particles. That's a kinetic process that we don't capture at the moment. And also how this would look differently if you had better, more accurate physics is a really interesting question. People will hopefully be able to do soon, but yeah. It's already pretty expensive computer simulations. So obviously doing this in a plasma context is really hard at the moment. And even in a non-ideal MHD context is really hard in 3 dimensions. Thanks for the question. So I don't exactly know the answer. I hope that the whole flaring process is set by sort of the eruption timescales, in which case you might expect that with a different reconnection rate or something else, it might actually look kind of similar. But that's I will continue doing this. But yeah, very hand wavy explanation. Okay, so one thing we've been doing recently for both the flares and for trying to push to higher accretion rates, we need to include radiation physics. So we said the cooling at these low accretion rates is very weak. But that's not true if we go to higher energy radiation from higher energy electrons. In synchrotron radiation, cooling will become efficient. And if we go to higher accretion rates as well. So I just want to highlight that basically for every system, we need to be including radiation. And this is something that we've been doing in our group recently, that even if you're at very low mass accretion rate, nowhere near 1 for this accretion parameter, the electrons can still cool efficiently. So the electrons are not actually coupled to the protons. And even though they don't exchange energy, if the electrons are heated, they can cool, they can radiate away energy. So we should include radiative cooling. And just an example from Monika Mostrobrodska is shown over here, old now, but this is for M87, just showing that if you don't include any radiative cooling, the radiated spectrum would be like this. And this is clearly different when you include cooling. And this is actually an unphysical amount of cooling over here. Okay, and so the way that we do this is we do radiation, GRMHD, where the radiation is captured by Monte Carlo methods. So you have little photon packets that travel around, and that lets you do inverse Compton scattering, which is the most important next radiation process as you go up in accretion rate after synchrotron radiation. Okay, so I'll just show briefly a couple of results from this. And I'll just comment that right now, the way we do this is still with a purely thermal electron distribution. So there's an electron energy in the calculation where the electrons can be heated and cooled, but we don't account for particle acceleration and energy dependent cooling of the electrons and other great things that we should do and that we're working on trying to do. Okay, but I can just show what a flare looks like, at least if you include cooling. And so this is work done by graduate student Michelle Lefay in our group, where the flare spectrum is shown in blue and compared to the otherwise one here. This is where the Event Horizon Telescope stuff is done down here. So this part remains mostly unchanged during the flares, but this part over here in the infrared and optical, you can see this large increase, and that's what we would call the flare. So that's an infrared flare that comes out of a calculation with radiation, but we don't get anything in the X-rays, which is actually where Sgr shows its largest amplitude flare. This is expected analytically that it's very hard to make this work from, this is Compton scattering. Just from Compton scattering, the densities are so low, it's hard to get a lot of amplification from Compton scattering. So we think this must be non-thermal emission that would then come out over to here where the flares are seen. And we've done that in post-processing, but not yet in a real calculation. Okay, and I just wanted to show there's one thing that has been of interest to many of us in the galactic center community, which is like, why don't other black holes show these similar flares? Even M87 doesn't seem to show any similar behavior as Sgr. So why in the world would that be? And so at least Michelle's current answer to this would be, well, radiative cooling is much stronger as you go up in accretion rate, and it just suppresses this flaring behavior. So this is a calculation of the same exact physical scenario, just with scaled to higher density to model M87. And you can see the blue does something kind of similar during the flare time. It's just not nearly as dramatic at, say, the infrared. It doesn't produce a whole lot of luminosity out here because the particles just cool. They cool much faster, and so they don't produce these large sustained flares. Okay. So that's my guess at the moment, is that if you go to other systems that are at very, very, very low accretion rate, like Sgr, you might expect to see that behavior. And for the vast majority of sources in the universe, we probably don't. Yeah.
So if you heat the electrons to gamma of 10 to the 3, then their mass is going to become comparable to the rest mass of ions.
Yep.
And MHD, at least the MHD I know about, you ignore the electron mass. But if the electrons become as heavy as ions, then maybe you shouldn't be ignoring their mass.
Yeah, it's a good question. So the way that we do this numerically is we have a single fluid. So we just have one ideal MHD fluid, and then we assume that the electrons and protons move together.
That's not necessarily the case.
Yeah, so I agree. This would be great to do better, but that's the approximation we're making now. And so in that case, it doesn't actually matter the relative energies, but I agree that, well, what we want to do next is do non-thermal particles.
They don't
What's
move
that?
together.
What's that?
There's a Hall term, which is the extent to which they don't move together, that can become important.
Okay, I'd be happy to talk about this more. I'm curious if in this context, if that is important, but I do think it's true that when we go to do non-thermal particle acceleration, we expect to have very high energy electrons. And then I'm not sure that they move with the fluid anymore. So I agree with the general concern, but that's how we do it today. Yeah, I'd be happy to talk about this more because it's something that we're trying to do. Okay, Great. Okay, so then, well, what happens at higher accretion rates? So the vast majority of sources in the universe we can't image, but are also at much higher accretion rate. So our idea as well, maybe we think we have some ideas of what might go on, at least at very, very low accretion rate. Let's just try taking the same physical paradigm and scaling it up in mass accretion rate. So as an experiment we did in this case for stellar mass black holes, where we just try turning on radiation and just keep increasing the accretion rate as high as we can go, basically to ask at what point do hot accretion flows collapse into thin accretion disks? When does the cooling become so strong that it changes the structure of the disk? Okay, so this is just showing, this was our, basically similar to what we've been showing, hot accretion flow, very extended here, and the radiation is from synchrotron radiation and some Compton scattering, but very, very, very close to the black hole. This panel, the colors are radiated cooling rate of the gas. And if we go up a factor of 100 or so in mass accretion rate from this, this is the highest that we can go stably with a hot accretion flow, we actually see that the structure starts to change in the way that we expect. So our gas actually starts to cool. Basically the Coulomb coupling energy exchange from protons and electrons becomes significant enough that the protons are able to cool by heating the electrons. And so now the overall gas pressure and structure of the accretion flow starts to change in a way that's similar to what was predicted by analytic theory. So you can see that on this density plot, the saturated white region here is high density starting to form something more similar to what we would call a thin disk eventually, although not there yet. Okay. The other interesting thing here is you can look at where we're getting cooling, and it's almost all from Compton scattering, and it goes out as far as we dare to plot things in the calculation. So the gas can cool at a wide range of radii from Compton's upscattering of photons that are produced very close to the black hole still. Okay, great. And we can cool the gas down to this temperature of 10 to the 9 Kelvin, sort of similar to that X-ray binary cartoon we showed at the very beginning. All right, so if we plot all these, then what we see that's pretty interesting is we can make spectra that look like the so-called hard states of black holes, the one that we showed in the cartoon. So this thing in blue, this is all a multiple Compton scattering spectrum now of seed photons were down here, and they get upscattered and form this, what we call a hard power law in black hole accretion. But this looks a lot like things that are actually seen in some X-ray or in a lot of X-ray binaries. So we start to get something that at least looks similar, whereas down here it looks more like, say, M87 or something like that down here. Okay, and something that is maybe surprising is that I said at the beginning that these hot accretion flows in general, they lose their energy to the black hole. They don't radiate it away, and so they should be radiatively inefficient. And at least in this model, what we find instead is that the radiative efficiency can be really high. So it goes up to 24% for this blue spectrum here, which actually exceeds the Novikov and Thorne disk, thin disk value at the same black hole spin. That's possible because we can get extra energy. Those calculations assume that there's no energy extracted either from the black hole or from inside the innermost stable circular orbit. So that's possible, but it's pretty interesting that both happens, and in a hot accretion flow where this isn't a thin disk where all the cooling is very strong. Okay. So apparently hot accretion flows can be radiatively efficient. Great. Okay. I should stop. And I would just say that this has been calculated previously in analytic theory, how this should look. And the results are consistent in that we generally expect that as you go up in accretion rate, the Compton scattering over here should become stronger relative to, say, synchrotron emission or other emission processes. But now we see this in a more self-consistent accretion theory. Okay, and what happens next? Well, the whole thing collapses. And we can't follow it because we're doing explicit Monte Carlo, and once the interactions become frequent, then we give up. But what we see is the collapse that we expect, where basically once the gas becomes really dense, then if you decrease the temperature going from red to blue in gas temperature in the top left, then the cooling rate actually increases because the Coulomb coupling becomes stronger and free emission also becomes stronger. As the density goes up, the cooling goes up, and that's going to keep collapsing the disk because that'll keep making the density higher and higher. So this thing will collapse, and we can't follow what it does next. So that will be very interesting to try to do in the future, but we need some different method. Okay, and the last thing I wanted to say is that complementary studies from our groups and others have tried to do approximate radiative transfer. So this is trying to do physically realistic radiation, which is possible at very low accretion rate. If you go to higher accretion rate, you need to approximate something. And I would say with strong magnetic fields, the results seem really interesting. So there's a couple of really interesting things that we and others will be exploring for what might happen in thin disk systems like the ones most people study. So one of them is shown here, where in this case, there are very strong magnetic fields. And you can see that the density of the gas, the disk itself is almost sort of truncated or disappears in this case from strong magnetic fields when at high mass accretion rate, calculation by Matthew Liska et al. And one that we did, led by Nico Seppi, a former postdoc in our group, showed that in this same case of strong magnetic fields in a thin disk, it looks like the whole way the accretion works actually changes. That instead of this turbulent torques on sort of small scales, large scale magnetic torques instead are what are actually taking angular momentum out of the gas. Okay, proposed a long time ago, but seemingly what we find again in this case of strong magnetic fields for thin disks. Okay, great. So I'll stop there and just summarize to say that I think we're making progress in accretion theory. The new sort of numerical theory we've developed based on MHD can produce accretion and also seems, at least so far, consistent with what we've seen in black hole images. So worth exploring. And I tried to argue that at least so far, interpretation of the polarized light in those images is that magnetic fields near black hole event horizons appear to be very strong, meaning dynamically important and can push back against the gas and influence the accretion process. And at least in our group, we're currently trying to explore what those models might imply for other systems and for flaring radiation. And in particular, we would like to know what happens, how do disks transition between these two states of being hot accretion flows and thin disks, and what do thin disks actually look like in nature. So thanks very much for your attention.
Any more questions that haven't already been asked?
What is a typical densities? You mentioned magnetic fields and temperature, but not the densities.
Yeah, so in the galactic center and M87, the densities are sort of of order like 10,000 to 10 million particles per cubic centimeter. So extremely low density. Another way to put it is that the mean free path is basically like the entire size of the Bondi radius.
So
Yeah.
you mentioned the hydrodynamic pressure, and magnetic pressure. What's the beta of that, the ratio of those?
Yeah, so in hot accretion flows, when I say strongly magnetized, that actually is sort of beta twiddle 1. It's not very small. And then in the more weakly magnetized case, the way we simulated, it's more like 10. So it's really not that different. But yeah, it makes a big difference in how things look.
So I have actually a question. So in the plot you had with the sort of mad disk and the infrared flares, you sort of had magnetic flux versus infrared luminosity. So the sort of characteristic time scale for the magnetic flux eruptions looks like it's sort of the Alfing crossing time across the box the simulation is being done in. So I guess the question is, do you think if you did a box that was 10 to the 4 RG instead of 100 RGs, is that part scale free, do you think?
Yeah, it's a good question. So the question is, a friendly rephrasing might be, what is this recurrence time here? And I would just say that I don't understand it very well. So what it looks like is, we know that it can change some amount based on different people doing simulations, but it's pretty much similar to this within a factor of 2 or something. But also we all tend to do pretty similar simulations. So I'm not saying it's not a physical theory. So I don't know. I've heard in the past, so it looks like it's a ramping up type thing, right? You expel this flux away, it needs time to then ramp back up. But I don't have a very satisfactory answer for how long does it actually take to ramp back up.
Just thinking, in principle, there's no particular scale except maybe the 1D scale, which is enormously bigger than that. But I mean, the question is sort of the infrared flares seem correlated with it. Of course, the infrared is picking out, where the cyclosynchrotron frequencies are in the infrared, so you might just see the inner flavors, but
Right.
like the magnetic flux itself might have.
Yeah.
Scale free.
Yeah, it's a good point. So I think what we see is that this erupting stuff tends to go out to some location, 10, 20 something gravitational radii, and then it kind of mixes back in. And so then, I mean, speculative answer would be that then reaccretes, right, and builds up the magnetic flux again. But I don't know, I think your question is like, well, is that
You have
radius?
the same process happening.
Yeah, if you
hundreds
just
or thousands of years.
make a much bigger box or something, will that process take place further away? So I don't know for sure. I can just say that this is run for a very long time. So actually over this time duration, the sort of region of the accretion flow that's in steady state changes by a significant amount. And the recurrence rate or the recurrence time doesn't really seem to change. But I agree that this needs to be understood. I would trust it as a number if I had an analytic, written down explanation of what is happening to set it. But I think it probably has to do with kind of mixing of this erupting material with other stuff and then reaccumulating. That's my best guess.
So for these problems, I guess you can take norm neutrino effects in terms of cooling or.
Yeah.
For neutron star mergers, this is very
Yes.
important.
Yeah, so that's a great, yes, we talk a lot about methods with neutron star merger people and about the rules of strong magnetic fields, and a lot of this is in common, but the relevant density scale is just incredibly lower here. So yeah, that's right. All these interesting effects of at high density, photons are trapped. Neutrinos can cool the disk. We're nowhere near there. The disk is completely optically thin to photons, and we don't know of ways to have neutrinos around, or at least I don't offhand know of ways to have neutrinos. Yeah, but a lot of the ways we do the calculations are very similar. So yeah.
Yeah, are you able to get away with some of these like this models that try to emulate the magnetic field? Because when you have magnetic field that severely restricts your CFL condition, drives up the computational cost, those kind of things.
Yeah.
Have you even looked at this?
Yeah, so the process supposed to be operating is sort of similar to a dynamo. And so people have tried to do sort of closures or approximate models to not need, especially like 3 spatial dimensions, time dependence. It's a real pain, but I don't know of any of that I would trust in the same way, I guess. And especially because so much of what we study and care about is the dynamics of the magnetic field. I feel like at some point you're kind of putting that back in. And so, but I do think that for a lot of applications, especially for interpreting observations, like I showed, it'd be wonderful to have simpler models. There's a lot of unnecessary systematic error that comes about, like I calculated all these images from my simulations, let's compare them all to data. That just invokes a lot of our systematic errors now are just built into the basic interpretation, which is to me undesirable. So yeah, I think doing things with simpler models in that context would be useful for trying to understand the physics of the systems. I don't know at the moment how to get around doing a full calculation.
Okay, I think we should stop it here. If you have further questions, you can come down and ask them, but let's thank Jason again for a great talk.
Thanks.